right, dear colleagues, so welcome to our seminar. I guess we can smoothly start. So it's my pleasure to introduce you our today's speaker, Dr. Rostislav Mikhaylovskiy. So a couple of words about him. He's actively working in the field of Terahertz Spectroscopy, investigating ultrafast spin dynamics. He received his PhD degree in physics from the University of Exeter in the United Kingdom back in 2013. Then he worked as a postdoc in the Netherlands in Radboud University. And now he's working at the associate professor position at the physics department of Lancaster University and develops his independent research track on ultrafast switching of magnetic order. So Rostislav, please, you are welcome. And I should briefly remind the rules of the seminar to our listeners. In case if you have any questions to Rostislav, please either raise your hand or you may type the question in the chat. You may also ask the question by voice, but please make sure not to interrupt the speaker just in the middle of the sentence. So please, Rostislav, the stage is yours.
Yeah, thank you very much for kind introduction and for giving me a chance to speak at this seminar. So the topic is already shown on the slide. So this is the Terahertz Spectroscopy of Ultrafast magnetic dynamics. But before coming to the actual results, so let me just tell you that the work has been done with the great support of Professor Alexei Kimmel and Professor Terahertz from Radboud University and many other colleagues from there. So I will also focus on the experiments done together with the group of Professor Rupert Huber in University of Regensburg, Germany, and Professor Zvezdin from Moscow provided important theoretical support. So here you can see the outline of the talk. So I will start with some introduction, giving the ultrafast magnetism into context of the current research. So then I will discuss why do we need to use Terahertz spectroscopy to look at ultrafast magnetic dynamics and give a couple of examples. So what new phenomena can be discovered with the Terahertz look. And finally, I will probably spend the largest part of my talk focusing on the new area of Terahertz control of spins. Okay, so let's just start and remind ourselves that magnetism is perhaps one of the strongest quantum effect manifesting itself on the macroscopic level. So you can, for example, compare the typical Curie or Niel temperatures, which can reach thousands of Kelvin, to, for example, critical temperature of superconductivity, another well-known macroscopic quantum effect. And here you immediately realize that they have like 1 or even 2 orders of magnitude difference. So the magnetic properties of materials mainly arise from electronic spins. So an electron has its innate angular momentum called spin. And it turns out that in many materials, the ordered state of spins, either parallel or antiparallel, is energetically more favorable compared to a disordered state. And the reason for this is the so-called exchange interaction, which is nothing else as the part of electrostatic Coulomb interaction, which depends on electron spins. So the energy scale of the exchange is about 10 millielectron volts, which entails the effective magnetic field, which we can assign to this interaction reaching up to 1000 Tesla, and we can estimate the precession time in such a high effective field, and we see that the time scale is about 100 femtoseconds, which may hint that magnetism is actually very fast. So the response time of magnetism can be very short. At the same time, it is a question, how can we actually control or drive magnetism at such a short time scale? Because the typical scenario envisaged, like say 20 years ago, would be that we take the shortest available stimulus, the laser pulse, and then we can excite magnetic material. But the electric field of the laser pulse primarily interacts with the electrons. The electrons can be quite fast in response. So then on the time scale of 10 femtoseconds, they can exchange energy with phonons, but then the phonons and the spins interact on a much longer time scale of spin-lattice interaction. So the conjecture was that the spins not excited directly, and then the time scale will be mainly determined by this spin-lattice interaction time. So the question was whether the faster dynamics can be attainable. And the question was answered in 1996. So when it was first shown that ferromagnetic metallic film of nickel was excited with the laser pulse, and then it was shown that its magnetization drops on the time scale of the 100 femtoseconds, and then it follows with the slower recovery. And moreover, about 10 years later, it was shown that the laser pulse can even excite coherent spin oscillations, and the phase of these oscillations is determined by the helicity of the circularly polarized laser pulses. And hence, the area of dynamics at shortest possible time scale was open. So why we started to develop the new technique, Terahertz spectroscopy, in the area of ultrafast magnetism. So let me start first with the kind of the basic experimental technique to study spin dynamics. So we have the so-called optical pump probe geometry when our sample is illuminated by a strong pump laser pulse, which produces some changes in the material or in its magnetic structure. And then these changes are traced using the weaker probe pulse delayed with respect to the pump. And we can essentially study the information about magnetization dynamics by looking at the polarization state of the probe pulse. So, for example, rotation of its polarization plane, which is proportional to magnetic order parameter, such as magnetization, antiferromagnetic vector, or in some materials, just some separate sublattices. So if the pump changes either one or several of these order parameters, so then it can be imprinted into the polarization change of the probe. However, as you can see, apart from the magnetic order parameters, we can also have this coefficient, which in principle can be also modulated by the strong pump excitation. So that means that at some cases, the results can be indirect or ambiguous for interpretation. And it led to long-lasting debates about the validity of analysis of these magneto-optical signatures of ultrafast magnetism. Examples we demonstrated or discovered ourselves. So we looked at the rather thick crystal terbium gallium garnet, which is known for its highest Faraday rotation, especially at low temperatures. And in the pump probe geometry, we observed a very nice oscillations, the frequency of which depends strongly on the applied magnetic field. So they're really reminiscent to the spin resonance oscillations, which one would expect. However, after careful analysis, we identified that actually these signals, which are similar to spin resonances, in fact have nothing to do with it. It is simply the transformation of the rotation of the polarization of the probe or the pump pulse inside the thick material with a very high Faraday rotation into the time domain. So it's kind of artifact of the pump probe geometry in such a system. So I don't want to go into the details of this study.
Rostislav, just to understand. So do I understand correctly that this intense pump, this induces spin polarization? So the sample is magnetized, and then when you check it by the probe, you retrieve something like Faraday rotation. It is still something of that kind, but the question is how fast the spins are reacting, how fast the magnetization changes, and this is reflected in the periods of these curves, which you are showing on the right-hand side.
Yes, so this would be the standard interpretation. So, for example, if we go back, so that's definitely the case here. So you come with the laser pulse, something in the material changes, like you have spin oscillations, and they imprint these oscillations into the Faraday rotation of the probe pulse. However, as I just tried to argue, so in this particular case, these oscillations, although they look like spin oscillations, they are not them.
Oh.
So what happens here, you have your pump and probe geometry. And because the crystal is thick, of about 1 millimeter, and its Faraday rotation is very high, for the strong applied magnetic field, the polarization of both probe and pump already makes several cycles, full cycles of rotation inside the material. So then you can have a situation when you pump is reflected back. So you come with the pump here, but then it reflects back. And at some point in the material, it meets the probe, depending on the delay. And then you simply have what is called optical Kerr effect, when the probe will have some additional polarization rotation based on the intensity of the pump. But the strength of this optical Kerr effect will depend on the angle between the polarization of the probe and the pump in the position where they meet. But position where they meet depends on the delay, tau. And the angle of between their polarizations depends on the position, because polarization of both of them rotates. So here, just for simplicity, only probe rotation is shown. And so that's why you essentially just see oscillations.
And so you can confirm this interpretation by measuring the spectrum with different incidence angles or something like that.
Yeah, so we did it for both collinear and like parallel, anti-parallel geometry, for example.
Right.
And so there are other features which allowed us to identify that these are not spin oscillations.
And then I have a question to the theoretical part. So it is quite well known that you cannot get magnetic response at high frequencies like optical. This is argued in Van Baum and Lifshitz. So I guess something similar should hold for magneto-optical. So high frequency magneto-optical response is challenging. So am I right? Or there are
you're right. So that's why usually when we consider the interaction between the laser pulses and the magnetic system, we essentially neglect the magnetic field of the laser pulse.
Mm-hmm.
Yeah, so this was just the illustration that even with this powerful tool pump probe, you can still have plenty of ambiguity or even artifacts.
So Rostislav, I guess there was a question from Mikhail Partnoy. Mikhail, do you still have a question?
Yes, I do. But can you probe at a different frequency to suppress this? This is apparently some interference effect and delay. But if you probe by not a coherent, not the same kind of laser, then you cannot do. I mean, that will be avoiding this artificial effect. Am I wrong?
I don't think. I think even if you will have the so in this pump probe delay, so you essentially transform it in this manner, but you can also imagine that your probe, for example, is CW laser,
Mm-hmm.
and then this will result in its modulation in the real-time domain.
Yeah.
Right. Okay. So now we go back to presentation. So alternative method to measure magnetization dynamics is Terahertz spectroscopy. So how it works? So again, we have the magnetic material, let's say magnet. So then we illuminate it with a strong pump pulse. So then we change its magnetization. But we also know that if we change magnetization at the very short time scale, let's say terahertz frequencies, so then this changing magnetic moment acts as a dipole, as an antenna emitting electromagnetic radiation at these frequencies. And we can then study this terahertz emission, for example, focusing it on electro-optic crystal gated by another laser pulse. And electric field of the terahertz wave produces optical axis due to the Pockels effect. So then the gating pulse experiences birefringence, again acquires polarization change. And this polarization change is proportional to the terahertz electric field. And by changing the delay between the pump and the gate pulse, we can record the time trace of the terahertz wave. And by analyzing the properties of this wave, we can reconstruct the emitting dynamics in the magnet. So essentially, as I will demonstrate, this technique serves as ultrafast magnetometer or ampermeter. So the first example is very simple one. So we just take the ferromagnetic film magnetized in plane, and then we can simultaneously measure the terahertz emission in response to the excitation with a strong pump at 800 nanometers, and the magneto-optical Kerr effect rotation of the weak probe pulse. So here we use the very same sample, the very same laser to produce all these pulses, and that removes any ambiguity, and we can directly compare the signals. So here you can see the MOG signal here, which is more or less similar to that observed in 1996. So we have the demagnetization and slower recovery. And here we can see the terahertz emission signal. So can we connect these two measurements? So assuming that this rotation signal represents magnetization dynamics, we can solve Maxwell equation for our structure and find the terahertz electric field emitted at the surface of the sample. So then we need to account for the transformation of the spectrum of our electric field due to the propagation in our optical scheme, and also convolve it with the response function of our electro-optic detection crystal. So here I show already combined spectrometer response together with the response function of the detector. And after doing so, we were able to reconstruct the spectrum of the emitted terahertz wave, so calculated from this Mach signal, and compare it with the measured one. And without any fitting parameters, you can see that they actually match very well in both shape and amplitude. So that actually shows that indeed, at least in this simple sample, just metallic film magnetized in plane, there is a sort of a clear connection between the magnetization dynamics and the Terahertz emission signal, and indeed the Mach signal in this system does represent the magnetization dynamics. But of course, this is nothing new in terms of physics. The fact that the ferromagnetic film is demagnetized by the laser pulse was well known. So we can now look at more complicated sample and see whether we can actually discover novel phenomena not observed with the standard pump probe technique. So instead of the single ferromagnetic field, we now looked at bilayers. So again, we have the, say, 10 nanometer thick cobalt film, magnetized in plane, vertical on this figure. And then we add a thin, maybe like 2 nanometers capping layer made of platinum, for example. And then it turned out that here, the circularly polarized laser pulse can excite the terahertz wave polarized along the magnetization of the cobalt film. Moreover, the phase of the signal is determined by the helicity of the laser pulse. So we also observed similar signals for other capping layers, such as gold, ruthenium, tantalum. And what is the most interesting is if we look just on the bare cobalt sample, so then this helicity-dependent emission component is almost negligible. So it actually took us the whole night to average this signal and to get it. And so essentially you can look at this as follows. So you have just 10 nanometers cobalt, and you see you practically don't have any signal. Then you just put 2 nanometers of a capping layer, say platinum, ruthenium, tantalum, and your signal increases by 2 orders of magnitude at least. I find this effect still quite bizarre in a sense.
So,
of course,
may I ask a bit naive question? So you mentioned that the polarization of terahertz pulse, so electric field, is parallel to the magnetization of the sample. So naively, I would expect like it should be some kind of orthogonal. So could you comment on that? Why this is the case?
Yeah, that's exactly what I'm going to discuss now.
Right.
Right. So, of course, we checked that the capping layer itself doesn't produce any signal. And also, if we take copper as a capping layer, we again don't see any signal, or probably it's just of the order of the one from the bare cobalt. We were just lazy to average it. So this is already hinting to the fact that the spin-orbit coupling plays a role, because the difference between the copper and all other capping layers here is that the copper lacks spin-orbit coupling. However, in order to indeed reveal the physical origin of this emission, we need to perform some symmetry analysis. So the first obvious thing is to reverse magnetization by the applied magnetic field. And as you can see, the phase of the signal changes sign with the rotation of the magnetization. So the signal is odd in magnetic field. Then we can also rotate the sample around vertical axis while keeping the applied magnetic field direction the same. And as you can see here, again, the phase of the signal changes. Note that in the second case, when the terahertz pulse propagates through the substrate, it suffers broadening due to the dispersion and absorption. But nonetheless, you can clearly see that here on the left, the signal goes down, then up, and down again, while on the right, it goes up, down, and up. So meaning that there is a clear change of the phase. So not only the signal feels the magnetization direction, it also feels the inversion in space. And this is a clear signature of electric dipole origin of radiation. So it's not the magnetization itself or magnetic dipole which emits this signal, but some sort of electric dipole or electric current. So what can be its origin? So we already know that the circularly polarized light can exert a torque on the magnetization. So it acts as an effective magnetic field proportional to the light intensity and the helicity of the laser pulse. And in our case, then it produces a small tilt of the magnetization in plane of the sample. And in the system with a strong spin-orbit coupling and with a lack of inversion symmetry, such a change of the magnetization would produce the electric current, the symmetry properties of which are identical to the properties of our terahertz emission signal. So from this, we could conclude that indeed what happens in these bilayers, so adding the capping layer to the magnetic layer breaks the inversion symmetry. And if we also have a strong spin-orbit interaction in the capping layer, so then we allow the what can be called ultrafast spin galvanic effect, which creates the current with this symmetry observed in the experiment. And that's why we can generate femtosecond electric current pulses in just simple magnetic heterostructures. And now you can see where this magic effect comes from, because if you just look at the simple cobalt film, so it's symmetric, and obviously no electric dipole is allowed in it, and then you just break the symmetry with the adding of the capping layer and allow the electric dipole effect. This is what we could see in the metallic samples. So then I will give you an example of Terahertz emission spectroscopy of dielectrics. So here our task was to try to demonstrate the ultrafast control of the exchange interaction, which is the most fundamental in magnetism. And here the problem is that even if you imagine that your laser pulse changes the exchange interaction, in principle, it would not result in any observable, assuming that your exchange change is rather small. The situation is different, however, if we look at the system with the counted spin alignment. So for example, in many antiferromagnets, there is an interplay between the symmetric exchange interaction J and antisymmetric so-called Zhelezhinsky-Maria interaction D. And then the equilibrium orientation will be some counting from the purely antiparallel alignment, and the angle of the spin coupling will be given by the ratio between exchange parameters D and J. So then you can immediately see that if the laser pulse changes either one, or both of these parameters, then the angle of decanting will be changed, and this will produce a non-zero torque on spins, and they will start to oscillate around the equilibrium orientation at the frequency of the so-called quasi-antiferromagnetic resonance. And as the resonance frequencies in typical materials lie in the terahertz range, so then we should be able to observe the oscillatory signal at the frequency of the antiferromagnetic resonance. So then we can again employ our Terahertz emission scheme to detect it. So as main funded antiferromagnets, so such as orthophyrites, iron borate, hematite. So here I show you just a few examples. We had studied many more. And indeed, in all of these samples, we observed Terahertz emission signals, which are just oscillations at the frequencies of the expected quasi-antiferromagnetic resonance. And again, just to emphasize, so these oscillations correspond to the oscillations of the canting angle in this material, and the canting angle is simply given by the ratio of the exchange parameters, and then the only way to excite this mode would be to change this ratio. So this is kind of a phenomenological picture, but what can be said about, so I see the question from Sasha.
Yes, please.
I didn't interrupt. Oh, sorry. I have a question, or maybe you're going to actually discuss it now. So in this model which you use, is this change of the exchange interaction or Janshinsky parameter, is it instantaneous, or what is the time scale of this change?
Yeah, thank you. So that's indeed the question we ask ourselves. So what we try to do, and that's, I think, also you can find in the paper or at least in this supplementary file. So we try to model our expected signal depending on the duration of the change of the exchange, and you'll find that the best agreement with experimental data follows when we assume essentially the change of the exchange on the same time scale as the laser pulse duration.
Okay. Mm-hmm. Thank you.
And in principle, well, of course, we did the model, I think, probably because the referees asked us, but you can already see it from the signals themselves that your excitation is practically instantaneous. So it's impulsive excitation because it's just, there is nothing and then immediately the oscillation starts. And there is no growing.
Okay, thanks.
Yes, so that's so this is kind of phenomenological explanation, but we can also think about microscopic mechanism for this exchange change. So we envisaged two possible scenarios. So based on the optical absorption spectra of these materials. So here it is shown an example for iron borate, but for other materials, the absorption spectra are very similar. So the main features is the strong charge transfer gap above 3 electron volt. And then there are also weaker so-called forbidden DD transitions corresponding to the transitions between the states, crystal field states of the ions. So before we had the photon energy of 1.5 electron volt corresponding to 800 nanometers of our laser pulse. So what can be the possible mechanism. So one is the off-resonant charge transfer. So when we essentially transfer an electron from oxygen to the iron, and obviously this changes the hopping and the super exchange in this system. However, we can also envisage alternative scenario because we are actually close with one of these DD transitions. We can simply excite a spin flip in the iron spins, in the iron ions, sorry. So in order to distinguish these two scenarios, we have to perform spectral measurements. So of course, there are some technical limitations. So we chose the transitions about 2 electron volt, and this shaded area is the range in which we will be able to continuously tune our laser photon energy. So here you can see the signals measured with the pump, with the different pump photon energy or corresponding wavelengths. And after extracting the amplitude and also correcting the data with respect to the different power or these photon energies, we can see that the amplitude of the excited spin oscillations matches perfectly the absorption band corresponding to one of these DD transitions. So which clearly indicates that this exchange interaction is perturbed due to the pumping of these DD transitions in iron ions. We also tried to pump in vicinity of the charge transfer gap at 400 nanometers, meaning 3 electron volts. However, in this case, we didn't observe any emission at all. Well, of course, we cannot rule out that in principle, in that case, the penetration depth inside the material was very thin, and therefore it could be that it was not sufficient to produce measurable signals. So we cannot, strictly speaking, rule out this scenario with the charge transfer. But at the same time, we clearly indicate that at least in the transparency region, the effect is dominated by the contribution from the DD transitions. So, in principle, we performed many experiments with the, yes, please, another question.
Yes, yeah, I have a question actually about this slide, and also it's a bit comes back to the previous question. So you told that it's instantaneous change of this one of these parameters, but what about some kind of a relaxation time? And do you see anything like a change of the frequency depending on the exciting photon energy? I mean, change of the frequency of the excited antiferromagnetic resonance, because it could be an indication that this altered exchange interaction stays there for some time after the excitation. So do you see anything like that?
Yes, so thank you for another interesting point, but we didn't observe any change in the resonant frequency. Mm-hmm. So I think it's more or less corresponds to the equilibrium one. And regarding the lifetime, I think you can also already see it from here. Okay. That the lifetime of this excited state is comparable to the duration of the laser pulse. Mm-hmm. Because I think if you take the, say, 40 femtosecond used in the experiment, the breadth of the spectrum will be comparable. Mm-hmm. So unfortunately, in such an experiment, it would be hard to distinguish very fast change in the parameters.
Okay.
I don't think there was any kind of long-lasting effect. So it's like excitation and then immediate relaxation. And especially since we look here at the quasi-antiferromagnetic mode with the frequency of less than 1 terahertz, so essentially what happens on the time scale less than 1 picosecond is very hard to distinguish.
Okay, thank you.
So of course we performed many Terahertz emission experiments. So I just gave you 2 examples. So there are others I don't have time to speak about today. Instead, I want to speak about other direction of our activity. So what is the common thing here is that we use this laser pulse with the energy scale of electron volts to excite spin dynamics, and this energy obviously exceeds the typical energy scale of the spin dynamics by few orders of magnitude, meaning that the largest part of the photon energy is actually idle with respect to the magnetization dynamics. It would be far more efficient to excite magnetization dynamics on its own energy scale. So can we do that at the same time keeping the ultrafast character of the excitation? And the question is yes. In that case, we need to use very short, but at the same time very strong broadband pulses in the terahertz frequency range. So here, the most obvious way to act on a spin would be the terahertz magnetic field. In contrast to the optical pulses, at such frequencies, we cannot ignore the magnetic component of light. And this magnetic field was shown to drive coherent oscillations in typical antiferromagnet nickel oxide, as was demonstrated in this paper. However, from the signal, we can see that this is just the oscillations at the background frequency, meaning that only linear regime was observed with a rather small spin deflection. However, practical applications such as spin switching or quantum computation would require nonlinear regime. So how can we achieve it? So the obvious way would be just to increase the amplitude of the magnetic field of the terahertz pulse, so as at some point it will be able to drive the system from one equilibrium to another in its potential landscape. However, in that case, magnetic field works against potential barrier, and the calculations show that the fields with the strengths of 10 Tesla or more are required, which is beyond the capabilities of the current sources of the terahertz radiation. Moreover, in an electromagnetic pulse, magnetic field doesn't come alone. It is accompanied by a strong electric field, which for the 10 Tesla pulse will be sufficient enough to damage the sample even before it can switch in terms of magnetization. However, what we can do, we can actually look at this electric field as not something parasitic, but actual effect. And because already with the much smaller amplitude of the electric field, we can hope to modify the magnetic potential to diminish the potential barriers separating different equilibrium states, making the system much more susceptible to nonlinear dynamics and switching. So one way to do it would be to find the low energy electric dipole active excitations coupled to magnetic order. So one of the example would be the orbital states that in some magnetic materials, magnetic oxide, set the magnetic anisotropy, so the energy which defines the direction at which spins prefer to be aligned. And then we can try to pump these transitions with the terahertz light and see whether this can drive spin motion. So in order to demonstrate this effect, we chose material called thulium orthopride. It has two antiferromagnetically coupled iron sublattices, which are also slightly counted, but that's not very important for us. What is important is that the direction along which spins prefer to be aligned is set by the orbital state of thulium rare earth ions. So as at the very low temperature, when the lowest sublevel of thulium ground state is occupied, the spins are aligned along the z-axis. However, as the temperature increases, simply due to the Boltzmann change of the population of the sublevels, at some point, the orientation of spins along the x-axis becomes energetically more favorable, and the whole system exhibits the so-called spin orientation between 80 and 90 Kelvin, when the magnetic structure continuously rotates in the xz plane, as I will now illustrate with the movie, which I will try to switch. So we start with the low temperature, spins along the z-axis. So now temperature increases, so the higher states become occupied, so the orbital state of thulium changes and the iron spins rotate. So this is, of course, quasi-equilibrium, slow process, but what we can do or try to do next is sit near the temperature of the spin orientation and repopulate the thulium states impulsively using our Terahertz pump. Since in that case, the orbital state of thulium is abruptly changed, it should exert a torque on spins and drive them into motion. So the question is how efficient this effect is. So here you can see our experimental geometry. So we have our sample illuminated by the strong terahertz pulse. And then we use a weak femtosecond pulse to trace Faraday rotation and hence spin dynamics in this material. Here you can see the time trace of the terahertz magnetic field. So the maximal field available is 0.3 Tesla. And the broad spectrum of the pulse covers both antiferromagnetic modes of iron spins and several transitions within the thulium ions. So here on the left, you can see the typical time traces of the Faraday rotation at different temperatures, so the signals are superpositions of two oscillations corresponding to two normal modes in this material. So the low frequency precessional quasi-ferromagnetic mode corresponding to the precession of the ferromagnetic vector with the constant length, and the high frequency quasi-antiferromagnetic mode. So that's one we already talked about, the scissor-like mode, which implies the change of the magnetization direction along the same axis. So obviously these modes are orthogonal as required for the normal modes of the system. So we can map, yes, another question?
Yes, but the motivation to use terahertz pulses with strong magnetic field is that you lose a lot of energy on the optical pulse. But how do you generate your strong terahertz pulses? Do you shine on nonlinear crystal short optical pulses? So from the point of view of energy, it's probably as expensive as the first technique, if you try to think about applications.
Yes, so in that sense, the energy is lost in the electro-optical conversion, so that I agree. But on the other hand, here we focus on the interaction of light with magnetism. And
yeah, I agree. So,
magnetic material.
The question is actually, I understand. I just wanted to check. So that means that if you want this control, you still need kind of coherent or incoherent cheap sources of terahertz radiation, which is not that energy consuming if you want to bring it towards applications. So it doesn't remove the question that you need other ways to bridge the terahertz gap. You need cheaper generation of terahertz radiation, do you?
Yes,
okay.
That's true, but that's not my concern. So here we can map the frequencies as a function of temperature, and you can see that precessional quasi-ferromagnetic mode is the soft mode, so its frequency goes to 0 at the temperatures of the phase transitions. So meaning that one may expect that this mode can be highly susceptible to the change of the magnetic anisotropy due to the pumping of the rare earth states. So what we can do now, we can sit within the spin instability temperature interval and start to increase the terahertz magnetic field. So here on the left, you can see the time domain signals, and on the right, their spectra. And should be noted that these signals are already normalized with respect to the driving terahertz field amplitude. So starting with the relatively moderate driving field, you can see that the signal essentially just contains the high frequency quasi-antiferromagnetic mode. However, as we increase the driving field, the signals change qualitatively, and another frequency component corresponding to the quasi-ferromagnetic mode arises in the spectra. And since the signals are normalized with the driving magnetic field, obviously it scales non-linearly with respect to the driving field. So we can even just plot the amplitudes of the modes as a function of the driving field, and you can see that this low frequency soft mode shows nonlinear scaling. So that's definitely not the excitation with the so it's not the trivial excitation with the magnetic field. Nonetheless, one may argue that the spin dynamics equation are nonlinear themselves, and maybe for such a strong magnetic field, the deflection of spin is so large that there is some nonlinearity in the system of the iron spins. So we did our calculations. So we took the waveform of our terahertz magnetic field and then solved the Lagrangian equation of motion for our ferromagnetic mode. And we found that for the field strengths used in our experiment, no deviation from linear behavior is expected, meaning that the effect observed in our experiment cannot be attributed to just simply isolated dynamics of the iron spins. Something needs to be included into the model in order to explain our results. So in this way, we can note that the crystal symmetry of our sample allows for the free energy term quadratic in terahertz electric field, which couple to the antiferromagnetic vector, which in this case is represented by the angle phi of the antiferromagnetic vector in the xz plane. And those familiar with magnetism can immediately see that this term has the symmetry expected for the magnetic anisotropy sinus square phi. And therefore, it just represents terahertz-induced change in this anisotropy potential. Moreover, it can be shown that this term can be allowed only in the temperature interval corresponding to the spin instability, exactly where we observed our nonlinearity. So that means that phenomenological explanation works, but can be connected to the microscopic pumping of thulium states.
So, Rostislav, sorry for interrupting. I have a short question regarding this expression for the free energy. So you do not include square of magnetic field because it's tiny and like negligible at these frequencies. So the contribution.
In principle, yes.
And then another question. So I missed this point, but if your unit cell is non-centrosymmetric, then you probably have to include products E dot B in terms of this kind. Or your unit cell is perfectly inversion symmetric.
Yeah, the crystal is inversion symmetric, so therefore the linear terms in electric field are forbidden.
Right, thank you.
So therefore we only can write it quadratic in electric field, but in principle that's what is needed to explain nonlinearity. Right, so what we can do to isolate the excitation of thulium from iron is that before our broad spectrum covered different possible excitations in thulium ions, also the antiferromagnetic modes. So what we can do, we can just cut away all frequencies in resonance with the thulium transitions, and if our interpretation is correct, then we just will observe the linear excitation of the ferromagnetic mode, no nonlinearity. So that's what we do. So here, light gray is the original spectrum, dark gray is the spectrum obtained after application of the low-pass Terahertz filter. And not surprisingly, in this case, the quasi-ferromagnetic mode is excited linearly with respect to the driving field simply by the Zeeman torque of the Terahertz magnetic field. In the complementary measurement, we can cut away all frequencies in resonance with the quasi-ferromagnetic mode, and despite in this case, this mode can be excited directly by the Terahertz magnetic field, it is nonetheless excited, and the amplitude scales non-linearly with the driving field. So that's kind of supports our interpretation that that's the pumping of thulium states mediates the nonlinear excitation of this mode. Meaning that the Terahertz pulse changes orbital states of the rare earth ions, they modify the magnetic anisotropy potential and exert torque on spins. And moreover, for the maximal field strengths of 0.3 Tesla or 1 megavolt per centimeter in terms of electric field, this anisotropy-driven torque is already 1 order of magnitude stronger than the Zeeman torque of the magnetic field. So the effect is not restricted to one particular material. We also observed it in other orthophrite, for example, dysprosium orthophrite, in which there is another kind of spin orientation phase transition in which another quasi-antiferromagnetic mode is the soft mode. And it, not surprisingly, then we see nonlinear scaling of this mode in this material. So then we also observe similar effect in other crystals such as iron borate, but I wouldn't speak about this now. So what can be concluded that so when we demonstrated this effect, it was the first observation of Terahertz nonlinear spin control, and this was a milestone on its own. But at the same time, you may notice that actually it falls short from our original goal, because we did observe the nonlinearity with respect to the Terahertz field, but there was no nonlinearity within the spin system itself, as the response simply represented the harmonic oscillations at the eigenfrequency. So what can we do to try to achieve the truly linear regime within the spin system itself? So, okay, let's do some simple calculations. So if we see it in the middle of the spin instability temperature interval, we can, at least in calculations, we can increase the amplitude of our driving field. So if we just take magnetic field, so then the field of about 11 Tesla will be needed to switch the antiferromagnetic vector into another equilibrium position. However, if we will rely on our anisotropy torque and it doesn't saturate, then the pulse with the electric field of about 1 Tesla will be enough to switch the spins as shown on this graph. So the model predicts all-coherent switching. The only question is, how can we enhance the Terahertz field? It should be also noted that although here, just for the sake of comparison, I'm talking about magnetic field, in this nonlinear anisotropy torque case, it's actually electric field squared, which is responsible to the anisotropy change, as was shown earlier. So what we may try to do is actually fabricate the plasmonic antenna on top of our crystal and enhance the electric field in the incident from the incident pulse, just increasing this electric field square locally in vicinity of this antenna. So the shape we chose was the so-called bow tie shown here, and this cap acts as an effective capacitor, increasing the electric field. So here you can see the enhancement. So for the 1 megavolt per centimeter incident field, you can locally get more than 25 megavolt per centimeter in the micrometer.
So, sorry, Rostislav, for interrupting. So do I understand correctly that here you're performing FDTD simulations, so finite difference time domain, because these are pulses, so, right?
Yes.
Because I didn't get the abbreviation. Looks like a misprint. So how many slides have you have left?
Yeah, I think it will be 5 minutes probably.
Okay, no problem.
Yes. Right. So this estimation showed that this field strength should be enough for more than 90 degrees spin switching. So what we first do, our Terahertz pulse is rather big, so it's much larger than the spot size is much larger than the antenna size. So it actually excites the big area on the sample. So what we can do, we can focus our probe pulse first away from the antenna and then within the antenna gap and compare the response. So here, black curve is just the response away from the antenna, and you can see that the signal is more or less the same as observed before in the previous part. However, if we focus our probe within the antenna gap, already for the smaller incident field, we observe much larger amplitude of this soft quasi-ferromagnetic mode. And what we can do now, again, we just focus the probe here into the gap and start to increase our driving Terahertz field. Again, on the left, you can see polarization rotation in the time domain. On the right, the corresponding spectra. So unless we reach the Terahertz driving field of 0.75 megawatt per centimeter, we still see these quasi-harmonic oscillations at the frequency of the quasi-ferromagnetic mode. But while we reach 0.75 megawatt per centimeter, the signal changes qualitatively. In the frequency domain, you have the splitting of the magnon band, which corresponds to the phase slip in the time domain. And as we increase the field even more, So these features become more and more prominent, and also the clear long-living step in the signal also appears, or that corresponds to the zero frequency component in the spectral domain. So now we can see that it's not the nonlinearity with respect to the driving field only, but there is a clear change in the spin dynamics itself, the change, the qualitative change of the response, and the splitting of the magnet band even is reminiscent to the Rabi flip, Rabi splitting for the quantum spin. So how can we explain these signals? So let's model the trajectories in the potential landscape. So here you can see the potential function for our antiferromagnetic vector, and we have two, for the given applied magnetic field, we have two minima corresponding to two different equilibrium orientations. So now let's assume we sit at the point within the antenna gap where there is a moderate enhancement of the field strength. So it's shown by the blue spot here. So then here you can see the trajectory. And in that case, the driving torque is not strong enough to bring the system into the equilibrium, into another equilibrium. So then we switch our attention to the spot at which the field is much strongly enhanced. And in that case, it produces the torque sufficient to bring the system into another equilibrium state. So then you may notice that if we plot these trajectories together, they become initially out of phase, but at some point they become synchronous again. So then if we convert these trajectories into the Faraday rotation for our probe and superimpose them onto each other, you already see that both in the time domain and the frequency domain, we get the features which we observed in our signals. And these features are fingerprints then of all-coherent spin switching, at least in some regions within our antenna gap. So here, this is kind of simplistic picture. What we can also do, we can, split, of course, our antenna gap into the region and calculate the trajectory into each of the points. So then we can convolve it with the Gaussian distribution of our probe pulse spot. And then we can reproduce all features of our experimental signals very nicely below and above this switching threshold. So essentially we can reproduce all the main features of the signals, which indeed shows that we did observe some fingerprints of Terahertz-driven all-coherent switching. This opens, of course, new ways to control magnetic properties of materials using different interactions in them. So then we can exploit exchange with the optical laser pulse. We can modify the orbital states which control anisotropy. We can try to drive phonons. So that's another exciting direction which I don't have time to speak about now. And this is essentially what we do now at Lancaster. We try to control different parameters and interactions in the magnetic materials in order to achieve the change of their magnetic state. So with this, I hope that I convinced you that Terahertz emission spectroscopy provides new important information about magnetization dynamics, and moreover, we can even use the strong Terahertz pulses to effectively control magnetic structures and even switch them in a coherent manner. And I would like to thank you for your attention.
Thank you, Rostislav. A very nice talk. So now the talk is open for questions. If you, colleagues, if you have any, please raise your hands. So in the meantime, I would ask the first question regarding the last part where you're discussing nonlinearity in response to terahertz field, and which is manifested through spin dynamics. So if you look at this nonlinearity from the point of view of nonlinear optics, which kind of nonlinearity do we have? Is it Chi2 or Chi3, or maybe some magnetic type nonlinearity?
Could you maybe a little bit elaborate your question?
Yeah, okay. So in nonlinear optics, when we discuss some nonlinear response of some materials, we normally assume that polarization is expanded in powers of electric field. Let's say we have linear response, which is proportional to electric field. We have quadratic nonlinearity, Chi2, which is associated with square of electric field. So polarization induced by square of electric field. We have this Chi3, which is polarization induced by, roughly speaking, by the cube of electric field, and so on. So can you classify your nonlinearity in this way? So I'm very interested in.
Yes, of course. So in principle, that's exact. So if we talk about the action of the electric field onto the magnetization, so then essentially it's the same expansion as you just mentioned, but the only difference is that your chi components will be also function of magnetic order parameter.
So magnetization, roughly speaking.
Yeah.
Yeah, that's interesting. So,
so you can look at it. I would rather, so that's, I personally prefer to follow like Blombergian and Persian approach when rather than expanding the polarization in terms of the electric field series, you should to expand energy. And then the different energy terms will simply correspond to different optical or magneto-optical effects. And in this case, you can immediately assign the direct and inverse effects.
Yeah, right. That's okay. But in free energy, this nonlinearity is manifested as which kind of terms? So do you have some terms proportional to e to the third power, or how this is manifested in the free energy?
So I think the simplest one would be simply m e cube.
Got it. Yeah, and then not prohibited by symmetry. Yeah, looks compatible. So I see there maybe.
But then you have m squared and so on. So it's,
there may be some question from Alexandra. So do you want to ask something?
Yeah, actually, if I may also, it's a kind of a question or comment about this discussion of nonlinearity. When you speak about nonlinearity, this nonlinear spin dynamics, typically people, and quite often people, especially from nonlinear optics, understand nonlinearity as the conversion of frequency. And here, is it maybe more proper to speak about non-harmonicity of the spin dynamics? It's not really any more harmonic oscillation, but it's rather the more complicated trajectory. Probably wouldn't be the more proper way to call this nonlinear, this spin dynamics which you observe in this last experiment.
Yeah, I think that's you may say it's on harmonicity indeed.
Okay.
So I wouldn't object that.
And if I may just also show a brief question. So this this change of the phase, which you observe in the experiment in these oscillations, so you explain it by a combination of the linear and nonlinear trajectories of spins. So this spin change, this phase change depends on the fluence, and it shifts to shorter time delays. So in the limiting case, when, for example, all spins follow this switching trajectory, what would be the trajectory which you measure look like in this case?
So then you would, so this phase slip would disappear then.
Okay, so it goes to zero basically, yeah, to zero.
Yeah, so it just corresponds, so it switches and then oscillates in the new equilibrium.
Okay, thank you.
Yeah, please, Mikhail.
Yes, some couple decades ago with your, I think Krugliak was your co-supervisor, we had a mini project on inverse Faraday effect. My question is related to this bow tie antenna. So that is a better geometry than what we proposed at that time, kind of ring-like and changing, you know, having quick currents induced by the change of magnetic flux through the ring, and then inversing magnetization and things like that. Did anyone, I don't know, I never done anything in that area for almost 20 years, but did anyone try eventually the circular geometry? Is anything better since you started to have optical pulses with non-zero angular momentum, or is it bow tie? Is what happened to the cell crossing? I'm sure you probably know this old papers.
Yeah, thank you for the comment. So that's, well, I'm not sure that that's fully relevant to the geometry you're discussing, but if you take the split ring, right? So then you can, so the bow tie, for example, here, it enhances electric field, but you can also take the split ring resonator, and then it will enhance the magnetic field instead. And these experiments were done, so there are a few publications, but apparently they are still not good enough to enhance the magnetic field into the nonlinear regime.
Okay.
So there were also, as far as I understand, the attempts to use also optical antennas, so not in the Terahertz range, but in the optical range, to enhance the field, the local field, and, for example, induce the switching in the metallic samples such as gadolinium and cobalt, and as far as I understand, with some sort of mixed success.
Okay, thank you. I just did not follow. Interesting that there was something at least tried. Thank you.
And then I had another question related, somewhere in the middle of your talk, you mentioned this photogalvanic current and associated effect. So where you discussed the symmetry properties, so the effect which was odd under inversion and also odd under time reversal. So can we go to that slide?
Let's go back. Yes, this one, right?
Yeah. So my question basically was the following: can we interpret this effect as some kind of bianisotropy? Because it looks like you have the emission of light with the electric field parallel to magnetization, and then formally we can describe this kind of stuff in terms of constitutive relations where electric field induces magnetization and magnetic field induces electric polarization. So I wonder if there is such a connection with bianisotropic media. Has anyone discussed some stuff like that?
Well, I wouldn't see there any source of bi-anisotropy, because the only optical axis here is the magnetization, right?
Yes. But bi-anisotropy means bi-anisotropic materials are such media where electric polarization can be induced by a magnetic field, and let's say magnetization can be induced by electric field. And they're always like made as a composite media. So here, as you mentioned, you break inversion symmetry intentionally by introducing this capping layer, or how you call it. So
capping layer.
by using a bilayer structure. So then it seems that from the formal point of view, this could be somehow related concepts. I'm not sure.
Well, I'm also not sure. So that's.
But nobody like discussed in the literature some connections of this kind.
I don't think so, because here again you can just look at this formula. So here sigma is, well,
it's handedness.
It's E squared there, kind of hidden, right? So J, or you can because it's in the at the high frequency, you can also essentially say it's also P, right? Polarization. So then you have M, E in polarization. So in energy, again, it will be ME cube, kind of.
ME cube, okay. And then my question is, does this structure provide some polarization conversion? Let's say you are pumping it by linearly polarized pump, you get linearly polarized response. So looks like.
No. Here we pump with the circular polarized light.
So the pumping is by circular.
While the Terahertz wave is linearly polarized.
Okay.
But of course, it's not because obviously there is a huge mismatch between the wavelengths, right? So it's.
Yeah, that's for sure. Okay, got it. Thank you so much. So I do not see other questions from the audience. So thank you for coming and delivering a talk. That's really useful for us. We had a nice discussion. So
thank you very much.
Thank you so much, Rostislav. And so I would like to announce the next seminar, which will be basically in 2 weeks, because the 23rd of February is a public holiday in Russia. So in 2 weeks, and we are listening to the talks of our PhD students, Yuri Mezinov and Daria Boychuk. So the same time as today. So stay tuned. See you next time. Goodbye.
Okay, cheers. Bye-bye.
Yeah, thank you. Goodbye.